Hi, YouTube. Well, this is my first video on YouTube, and well, I kinda wish that I can find some references when I'm doing my revision in the future, and also trying to make this logical pattern more apparent. So I decided to upload this very basic exercise of category theory on YouTube so that you can try to see if there are audience who would like to give me a little bit of advice for my write-up or like advice on my logic or something because well, one of the difficulty I study is really just to like detect the paradox I run into, and often it is harder for myself to really see the mistakes. That is really crucial. So I think that it's not that bad just to upload my like videos on the internet, so like people can really just judge and provide me like feedback, for which is pretty important for the learning process. So we're actually showing like a very classic result. So so IP and mono, they like a function, like a mapping that is both mono and epic. It is not necessarily like isomorphism. Well, this is very clear in this case because N is a proper subset of Z. So clearly that there cannot be an inverse of F. So that like by the definition of the isomorphism, so we don't have an inverse, so this thing cannot be isomorphic. So what is left to show is that F is both monomorphism and epimorphism. So recall the definition of monomorphism. So F is mono, then G equals to FH implies, so this propositional stuff implies G equals to H. So the thing is here, one thing that we can really leverage is the property of this. So because N, well, I know actually there should be way using a set theoretic method, but I don't think it's gonna be as easy as this, or maybe I'm just overcomplicating, but I don't know. But I think this is actually a very clean idea in terms of showing this using the freeness. So because this thing is free, so this mapping to say let's say because we have this assumption that this thing holds, so F G1 so that this thing equals to F H1 at this moment, this thing determines a unique monoid homomorphism. So because G1, I'll just make it a little bit simpler. Instead of making it G, I'll make it alpha. So alpha G1 equals to alpha. This is immediate. We have Gn equals to alpha n for all. This is a direct application. So like once you have fixed this element 1, and it fixes as a unit or something, so you have determined this monoid homomorphism uniquely. So it is unique. So and it is not only unique, but it matches this for every n. Because if you have to think of it, because by the definition of a monoid homomorphism, so it has to pursue the structure. So 1, let's say 2, that is basically G1 plus 1, because this is a binary operation. So we have G1 G1, so which is alpha square. So this thing is unique, and because this assumption that we have, because of this assumption, and that we can fix this unique monoid homomorphism. This implies, I'll make a definition. So this implies Gn equals to H of n for all n. And so this is one part, right? And now we suppose, we have to show that it is epi, right? Yes. And now our task is really to show, but like the thing is, it's funny that there is a symmetry here. The symmetry, this thing is a free monoid, and this thing is a free group. So suppose that H f equals to G of f. What will happen? So because like those things, those are those are from this free group to whatever the thing that it wishes. It doesn't matter. But whenever we maps f1, well, it doesn't even have to be f1, I guess. This will determine a very unique group homomorphism, and it also implies for every value of this, we will always have no, it's like yes. So because this thing is unique, this is a unique group homomorphism, and because G and H agree on the generator F1, so they agree on everywhere else. So they agree on everywhere else. So from this, like from the beginning of our assumption that HF equals to GF, this proposition will imply that H agree with G for all the value, for everywhere. I mean, like, well, because F here, as we have been saying, that F cannot be surjective, but this doesn't mean H and G are not surjective. It can be perfectly surjective function. It doesn't matter here. What matters is that the uniqueness. Whenever we have this little map, so this map maps into like this function that determines a very unique. It doesn't even have to be f1. It can just be a star or whatsoever. But I'll just use f1 because that star is not really defined. So this thing determines like a unique group homomorphism, and that they agree as this generator. So they agree on elsewhere. This is also the free property. Well, they're actually pretty similar in a way. You can think of it as a set X, and it's contained in a group F, and there, say, like a phi. So there's a unique group homomorphism. The thing, I think it should be, yes. So exist phi prime. So this thing will extend unique group homomorphism, and essentially that we're saying, say, define all map from X to G. We just make it like this, and so there's like a one-to-one correspondent to this set. This is group, right? F and G. So we're just saying this, and so because of this free group property, that we are able to say that we can conclude this proposition, and because of this proposition, we can drive like a conclusion that this proposition implies this proposition, and that we have shown that F satisfy Fg equals to Fh implies G equals to H, and Gf equals to Hf implies G equals to H. So F is both mono and epi. But F is not isomorphism because it cannot be isomorphism due to this fact. I think that this proof is actually pretty easy in a way because it doesn't really leverage a lot of analysis. It's pretty just conceptual. Like as long as one recognize the importance of those free generated stuff, like or you can basically think it as a more advanced structure. You can think of it as a, how should I say this? You can think like a group as a degrouping of like a one object category with automorphism group of it for this. Well, there's are layers of relations to interpret this thing, and often that they are similar in a sense, but like they are not really similar essentially. Like in category theory, like this free property, and that they are this uniqueness can be used for actions. Was a little bit more complicated too because my English skill is a little bit not well, but using those properties very well, it can be very powerful in terms of proving a lot of statement. Because as we have said, that it is also like a group-noid with one object. So one object category with an automorphism group of C. So in this case, that we will have a lot of possibility that it agrees on the subject is some sort of uniqueness, and that and because of the group property that we can also have. Well, this is just nonsense at this point because it's not even relevant to this question as of now. But in any case, this should be the proof. I think I'll just do like another one. I don't even know because I have been doing quite a lot of puzzle. I guess that's to be it because I still have like a class tomorrow, and this is my first video. And if you have any like suggestion or feedback so that I can improve, please don't shy away your comment, and I appreciate that so much. And thanks for your time for watching, and enjoy your day. And thanks so much. Bye.